Okay, so let's continue with the lecture. This is section 5.6, and we'll talk about rational functions. Now, there's some notation I want to show you. Okay, we talked about the arrow notation. So this is table 5.6 from your book. Okay, so here's what we talked about. That is x is approaching a from the left. Okay, so x is less than a, but very, very close to a. This is from the right. As x is going to infinity, that is, it's increasing without bound is another word to say that. Or going to negative infinity, that's decreasing without bound. Okay. And then again, you can have the function doing that, going to infinity or negative infinity, or the function itself can approach a certain value. Okay. Now, here's a synopsis of what we just talked about. This is our basic 1 over x. Okay. So you can see the different parts. That is, x is going to 0 from the right. The function is increasing without bound. Here, as x is going to 0 from the left, the function is decreasing without bound. Okay. Here, as x is going to infinity, the function approaches 0. And as x goes to negative infinity, the function is also approaching 0. And so that's where we put in these equations of the asymptote. One is vertical, and that is the x equals 0 line. And that horizontal asymptote is the equation y equals 0. So we'll need to keep these in mind. So let's say, for example, to just get a little bit more used to what just happened. Okay, there we go. Arrow notation. Let's say we have a rational function. Here's our x and y axis. And we have a vertical asymptote, the line x is equal to 2, and a horizontal asymptote, if the line y is equal to 4. Okay. Now, graphs will behave erratically around asymptotes, but one thing we could say, it might look like this, and it might look like this. Okay. There's no guarantee that that's what will happen, but it could look like so. Now, if we were to talk about arrow notation, one thing we could talk about then is the behavior of the graph around this asymptote x equals 2. Okay? And you can see it acts differently on the left of x equals 2 than it does on the right. So what we could say is x approaches 2 from the left. Okay? Then our function values are diving, so as I'm coming at it from the left, the function values are diving, and they are headed to negative infinity. On the other hand, as x is going to 2 from the right, okay, so here's 2, I'm coming at it from the right-hand side. As I'm moving to the right-hand side, the function's taking off to positive infinity. Okay. To positive infinity. Then we also like to ask ourselves what happens as x is getting extremely large. That is, what's happening as x gets very, very large, what is the function doing? So here's my values of x and going to infinity. As I head to infinity, these y values are bounded here by this line y equals 4 because it's an asymptote. And we could also ask about what's happening as x goes to negative infinity. Well, the function there again is also bounded by the asymptote. So here's x going to infinity. And as I do that, the function is getting closer and closer and closer to a value of 4. All right. So I hope that makes sense. Okay. Let's use translations now. Of our function f of x is equal to 1 over x. Okay. So we know f of x being equal to 1 over x has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0, and looks like so. Now, let's consider a new function, g of x, that is 1 over x plus 2. So, how is that going to change things? Well, what's happened here is that I've altered our basic 1 over x by adding 2 to the x values. So again, we'll use Lars, and since I'm adding, I'll be going to the left. Okay? So this whole graph needs to shift to the left 2 units. So what does that mean? Well, every important point needs to move, including this horizontal asymptote, okay? Because it's no longer x equals 0 that makes this denominator go to 0. It's x equals negative 2. So first I put that in. Now the horizontal asymptote will shift over as well, but shifting over doesn't change the location of it. So it stays where it's at y equals 0. Okay. And then every point needs to shift 2 units. So what that means then is it looks like this. Okay. So this is the graph of the using translations of 1 over x plus 2. Okay. We could change it further. What if we had a new function, h of x, which is equal to 1 over x plus 2, and then we added 3 to it? Okay. So I'm just going to put that 1 over x plus 2 back in so we can see this happen. This is x equals negative 2. The horizontal asymptote stays the same at y equals 0. And the graph looks like this. But now we've added a constant here. And adding this constant is going to shift everything up 3 units. Okay, so what would that look like? In this case, moving everything up 2 units will also move this horizontal asymptote up, 3 units. So now instead of being the line y equals 0, we have the line y equals 3. Now shifting up this vertical asymptote won't change its location. So it'll stay at x equals negative 2. And now everything shifts up. So it would look like this. So knowing those translations absolutely helped us to quickly be able to sketch. We can talk about domain. Let's talk about domain. Okay. So in this case, the domain, the only value we have to exclude is when the denominator goes to 0. So it's the set of all x such that x cannot equal negative 2. Okay. We could also talk about the range of this function. This range is the set of all y such that, well, there's only one y value we throw out. Y cannot equal 3. So in general, when we're talking about the domain of rational functions, the only values we have to exclude, okay, now remember a rational function can be written as some p of x over q of x, okay, where these are both polynomials. And that the denominator, whatever that function is, cannot equal 0. So, this is what we have to worry about in domain. We need to, number 1, set the denominator equal to 0. And then we'll solve for the x values. That make this equal to 0, and then we'll exclude those x values. From our domain. Okay? Everything else will be fine. Alright, so for example, let's find some domains. Okay, so let's say we have f of x is equal to x plus 3 over x squared minus 9. Well, the numerator is already factored. This is x plus 3. The denominator can factor into x plus 3, x minus 3. Now, this is going to get a little confusing. From here, we see that x cannot equal plus or minus 3. So the domain of this function is the set of all x such that x cannot equal plus or minus 3. Now, it is true, though, that this function is not written in lowest terms. This x plus 3 will cancel here. And this acts like this function x minus 3. Okay? But we still have this domain restriction. Okay? So we're going to talk about this in a little bit, in just a little bit. So even though this reduced function does not have a problem when x equals negative 3, the original function we're talking about does. Okay, so always work with this original when you're determining domain. Here's another one. Okay. So if we had a function that was, say, 4x over 5 times x minus 1 times x minus 5. Okay. It's very nice that this is already factored for us. Okay. From here, we can read that if x is positive 1, right, then we get 1 minus 1, which is 0, and 0 times anything would go to 0. So x cannot equal positive 1, and x cannot equal positive 5. This 5 doesn't affect anything because 5 never equals 0. So our domain is the set of all x such that x cannot equal 1 or 5. Okay. So let's look at an example of how we're actually going to graph these things. Okay, say for example we had to graph a function that's equal to x squared minus 1 over x squared minus 2x minus 3. Okay, so let's first factor this. This is x plus 1, x minus 1 over x plus 1, x minus 3. Okay. Alright, so we see that this is not in lowest terms. We could cancel these x plus 1s. Now before we go canceling, let's write down what our domain should be. Okay? Because we're concerned about the domain of the original function. So the values that make the original function's denominator go to 0 are that here if x equals negative 1, and from here if x equals 3. Okay. So this acts like this reduced function x minus 1 over x minus 3, except this is the domain for it. Okay. So what we're going to see happen here is that what will happen is that this value that we were able to cancel will lead to a hole in the graph, while the one that isn't canceled leads to an asymptote. Okay. Now let's think about the important points that any graph needs. Okay, so we need to know our x-intercepts. Now, it'll be easier to work with the reduced function. Okay? So we want to know x minus 1 over x minus 3, this reduced function. When does it equal 0? Because that's how we find x-intercepts. Okay? And then we can multiply by this x minus 3 on both sides to get them out of the denominator. So we have x minus 1 equals 0. So x is equal to 1, and so that leads to an x-intercept of 1, 0. So that's our x-intercept. Now for a y-intercept, again, we can use the reduced function. That's what we have to find the function evaluated at 0. Okay, well, if we're using the reduced function, that's equal to 0 over minus 1 over minus 3, which is negative 1 over negative 3, which is positive 1/3. So our y-intercept occurs at 0, 1/3. Now we also need to talk about any vertical asymptotes. So that is when the denominator, and we'll just use the reduced function. Okay, so when does x minus 3 equal 0? When x is equal to 3. So that will be our vertical asymptote. What about our horizontal asymptote? Okay. Now remember, horizontal asymptotes occur, let me just put this back up, when we are examining very, very large values of x or very, very small. Same here, very, very large or very, very small. So what we have to think about then is, how will this graph behave, x minus 1 over x minus 3, if x gets really, really, really large? And one way to do that is we look at what the dominant term of the numerator and the dominant term of the denominator are. So as x goes to infinity, this becomes infinity minus 1, so that's still some type of infinity, over infinity minus 3. And that is close enough to the same infinities that what we have is we can just look, the horizontal asymptote will be a y equation, and we take the denominator, or the leading terms of the numerator and the denominator, and reduce this. So we find that we get a horizontal asymptote at the line y equals 1. And we can go back and look and see if that applies to us as well. Okay. Now here we had something a little bit different. Okay. By adding 3, the asymptote comes up to 3. Right? And I will show you how we do that. Let's look at the first ones first. Okay. Now this is our rational function. Okay. So if we were looking for a horizontal asymptote, it's the line y equals something. Okay. And here, we can't just reduce this, so we have to think, well, what's happening? Okay. So as x is 10, we get 1/10. As x was 1,000, we got 1 over 1,000. When x was 1,000,000, we got 1 over 1,000,000. And from there, we saw that that led to this line y equals 0. And that's specifically because this denominator is stronger than the numerator. Okay. So we worked that out on the sheets. Okay. And we can look at this side again. Here we had 1 over x plus 2. Again, if we just take the dominant terms of the numerator and the denominator, that's just 1 over x. And then we think about what happens as x gets very, very large. Again, it went to y equals 0. Okay. I should really draw. It means we get y equals 0. We should really draw it like that. Okay. Now here, on the other hand, things changed. So notice that we wrote this so it was easy for us to do some translating. Okay. What we really had was a rational function plus another constant. But we could write this as a rational function by putting it over 1. And if we get a common denominator, that will be x plus 2. Okay. So this is equal to, x plus 2 is now our common denominator. From here, we take the 1. Okay. And from here, we take the plus 3 times the x plus 2. Okay. And now simplifying this, we get 1 plus, we need to distribute that 3 through, 3x plus 6 over x plus 2. Okay. And now simplifying this a little bit more, we can combine the like terms to get 3x plus 7 over x plus 2. Okay. And so now if we think about the horizontal asymptote, we know it's going to be a y equals line. The dominant term here is 3x. The dominant term of the denominator is x. And when that reduces, we get the line 3. Okay. So that is how that came out. Okay. So that is what we used here, the dominant term x over x. So we'll get a horizontal asymptote at y equals 1. Okay. Now let's try and put all this together and see what we're actually looking at. So here's our axes. We get a horizontal asymptote at y equals 1. Okay. Remember to label these with equations. And we have a vertical asymptote at x is equal to 3. Okay. And then we have this problem in the domain also at negative 1. Okay. Remember, negative 1 cannot be in this domain. Okay. So let's plot what we have. We have the x-intercept at 1, 0. And the y-intercept at 0, a third. So that's approximately here. Okay. And now we know 2 points. So basically we have 4 different areas of the graph. Okay. And we only have to be concerned with 2 at a time. Now we know that the graph can't be up here and down here because we'll have function values that are in the same spot, and then it wouldn't be a function. So we can assume then from here that as a sketch that this graph will be bounded in between these 2. Okay. But there's a problem when we get to negative 1. Okay. That actually leads to a hole in the graph. That is, the function just doesn't exist there. And so we can wonder what the equation of this hole would be. And to do that, we'll find we're going to have to evaluate the function at negative 1. Now we can't use the original function because we'll get 0. We'll get a 0 in the denominator. So to do that, we're going to have to use this reduced function. Okay. So it'll be negative 1 minus 1 over negative 1 minus 3, which is negative 2 over negative 4, which is positive 1/2. Okay. So the coordinates of this hole are negative 1, 1/2. I found that by using the reduced function. Okay. Now, that's not all there is to the graph, okay? Because the domain is everything but this negative 1 and 3. Okay? So there is a graph on this side of 3. We just have to figure out, is it going to be up here or is it going to be down here? Okay? So to do that, again, we can use the reduced function. Let's pick some value, say 5. Something to the right of 3, and we'll find f of 5, which is 5 minus 1 over 5 minus 3, which is 4 over 2, which is 2. Okay. So at 5, the function value is 2, which is above our asymptote. And from there, as a sketch, we will infer that the graph will look like this. All right, now let's ask ourselves, what's happening as x is going to, let's look at our negative infinity. Okay. As x is going to negative infinity, well, the function values then are approaching this y equals 1. Notice as x goes to positive infinity, the same thing is happening. We could ask what's happening at the asymptotes as x goes to 3 from the left-hand side. Okay, so to the left of 3, as I go towards 3, the function dives, goes to negative infinity. On the other hand, though, as the x is going to positive 3, the function is taking off to positive infinity. But we can also ask about this other domain restriction here. What happens as x goes to negative 1 from the left? Okay. Well, as x is going to negative 1, we're getting closer and closer to this value 1/2. And the same thing's happening as x goes to negative 1 from the right. The function value there is 1/2. The function doesn't exist there at 1/2, but the function is approaching that value. Negative 1 from the right means the function of x is going to 1/2. Okay? Okay. And so this leads to an idea about continuity. So in this portion of the graph, from 3 to infinity, there is absolutely no problem with the graph. It's nice and smooth, so it is continuous there. Okay. But if we look at the domain, let's just say from 0 now to infinity, the function, I would actually have to stop, and it breaks. Okay. So there is a discontinuity here in the graph at x equals 3 because of the break. Okay. Now if we look at the function on the entire domain, here it's continuous, it's very smooth, but when we get to negative 1, there is a break in the graph. And so it is a discontinuity there. Okay. Now it's not the same kind of discontinuity that this is. Okay. So this is discontinuity. Okay. This is a discontinuity. However, this one is a removable discontinuity, okay? Because it's just that one little hole, and we can use the function, the reduced function, to find out what value the function itself is approaching. Okay? So holes lead to removable discontinuities, and asymptotes are just simply a discontinuity. Okay. Now let's do another one so you can see this happen. Now, if we have f of x is equal to x minus 2 over x squared minus 4. Now, if we factor that, we get x minus 2 over x minus 2 times x plus 2. Right, so first of all, let's determine the domain. So the domain for our original function, f, is the set of all x such that x cannot equal plus or minus 2. However, this function is not written in lowest terms. Okay. This x minus 2 will cancel, so we get this reduced function of 1 over x plus 2, which we had graphed earlier. But it has this domain. Okay. So now this is just the translation. We've done it before. Okay. However, we also have to exclude this x minus 2. So we saw that this has a vertical asymptote at x is equal to negative 2. The denominator is dominant, so as x goes to infinity, the asymptotes the horizontal asymptote goes to y equals 0. And then this side will happen like this, and this side will happen like this. However, we're going to get a problem when x is equal to 2 from the domain. There's going to be a hole there. Okay, because 2 is the removable discontinuity. It came from here. All right. So what's the coordinates of this hole? Well, we can put it into our original function, and we'll get 1 over 2 plus 2, which is 1/4. So the coordinates of this hole are 2, 1/4. And now we can ask all our limit questions, or our x approaches questions. So as x approaches negative infinity, the function is approaching the horizontal asymptote at 0, and the same with positive infinity. Now, here at our discontinuity, x approaches, we can ask about negative 2 from the left, and x approaching negative 2 from the right. Okay. Well, as x goes to negative 2 from the left, the function value is diving. So f of x is going to negative infinity. And as we go to negative 2 from the right-hand side, the function is going to positive infinity. So the graph behaves differently. It's heading in different directions. Okay. Now, on the other hand, we could ask what happens as x just approaches 2. So if I look at that, just means I'm looking from the right and the left-hand side. And the function's value is approaching the same thing, up 1/4. Okay, so that's how we deal with all of these x approaching values, and how we deal with domain restrictions. They're either going to lead to a hole, which is a removable discontinuity, or we're going to get the asymptote. Okay, now asymptotes that are vertical can never be crossed. Okay? Horizontal asymptotes, when we're talking about them, we're really talking about what happens when x gets extremely large or extremely negatively large. Okay, so in that case, we're actually going to get 3 different cases. Okay. So let me show you 3 different cases. All right? So here's an example of one of them. Okay. So notice here we have a horizontal asymptote of y equals 0, verticals at x equals 1 and x equals negative 5. Okay. But the graph does cross this this horizontal asymptote. Now, vertical asymptotes can never be crossed. But these horizontal asymptotes, because we're really talking about extremely large or extremely negative values, they can cross in between. Okay. So that is perfectly acceptable. Because it's not an extremely large value. Okay. Now here the horizontal asymptote is y equals 0. So what that means is that in our rational function, the degree of p was stronger than q. So the degree of the denominator, was less than. The degree of the numerator was less than the degree of the denominator. So this could be something like an x squared over an x cubed. Okay, so the denominator would dominate, and when that happens, it pulls the asymptote to 0. Okay. Here's another case of what can happen with a horizontal asymptote. Okay. Again, we have a y equals 3 horizontal asymptote, and we're really just talking about the very end values, okay, the end behavior. So what it could happen, the vertical asymptotes can never be crossed, but this horizontal could cross it and then approach that asymptote from underneath. Now, we get horizontal asymptotes that are not 0 when the degree of the numerator is equal to the degree of the denominator. But here's a third case. We could actually get what's called a slant asymptote, and it has an equation of a line. Now that's going to happen, that you'll get a slant asymptote that is a linear line, okay, if the degree of the numerator is greater than the degree of the denominator, but only by 1. Okay, so if this was x cubed over x squared, if this was x over a constant, something like this. Okay, so those slant asymptotes will occur. Okay. All right, so let's see then if we can identify asymptotes. Let me refocus this. There we go. Let's see. Okay, so identifying asymptotes. Okay, so for example, let's say we have g of x, which is equal to 6x cubed minus 10x over 2x cubed plus 5x squared. Okay, so let's say that's it. All right, if we're going to have, let's look first at the horizontal asymptote. Okay. Horizontal asymptotes will have an equation y equals, okay, and we need to look at the dominant terms. Okay, so the dominant term is the 6x cubed. It's stronger than just an x. And the same with the numerator, or the denominator. This is an x cubed, this is an x squared, so the x cubed is dominant. Okay. And now we'll simplify this. Okay. The x cubes will cancel and 2 goes into 6 3 times. So in this case we have a horizontal asymptote of y equals 3. Okay. Now we're going to ask about vertical asymptotes. Okay. So let's factor this to make sure it's in its lowest term. So up top I can take out a 2 and an x, leaving behind 3x squared minus 5 minus 10x, 6x cubed, yep. And down below I can take out just an x squared, leaving behind 2x plus 5. Okay. So there's a little reducing that we can do here. I'm curious to see how this is going to work out. So this is 2x over 3x squared, or I'm sorry, 2 times 3x squared minus 5 over x times 2x plus 5. Okay. Now from the original, we know that the domain here is the set of all x such that x cannot equal, well, from here 0, and it's a double repeated, and here if I subtract 5 and divide by 2. So this is going to lead to, because there was no canceling with it, an asymptote, vertical. And I'm curious now, we also have from here that, so there's an asymptote here in the reduced function, and there's an asymptote, should be here at x equals 0. We should also get a vertical asymptote. The trouble is that this was repeated, so any canceling, I think the should lead to a whole, but since this is still here in a double root, it should be a vertical asymptote. So let us double check, and let's ask Desmos to double check our thought process here. Okay. So we need to put in, I just lost it. quantity 6x cubed minus 10x, and then that, so there's our cubic that we just learned about. Now we're going to divide that by 2x cubed plus 5x squared plus 5x squared. And close that. Yeah, and so from here we can see that because the x still hangs out, and it was repeated, then there'll be a vertical asymptote at the line x equals 0. Okay, so there's that. And then we also had, oops, not that. And then we also had a vertical asymptote when x is equal to negative 5 halves. Yeah, negative 5 divided by 2. So there's that asymptote. And then we can put in y equals our horizontal, which was y equals 3. Okay. Then I can make it a little bit larger, and we can see how that graph comes in and out of play. Okay. So in this case, we didn't get a hole in the graph because this is a double root, right? And it remains in the original, in the reduced function. So it leads to a vertical asymptote. All right, now let's do another one. Okay. Now, let's see here. What if we had, for example, say some k of x was equal to x squared plus 4x over 8 minus x cubed. Okay. Now again, we're going to look for what are we going to look for first? Horizontal asymptotes? Yeah, let's look at it. Oh, so our vertical asymptotes up here, where x equals 0 and negative 5 halves. Okay. Now, for a horizontal asymptote, it's going to come in the form y equals something. Okay. So I look at the dominant terms of the numerator. The dominant term here is x squared. Okay. And then I want to look at the dominant terms of the denominator, and the dominant term here is minus x cubed. Okay. So if we were to reduce that, let's bring the negative up top. We have 1 over x. Okay. But then what happens is x gets large. This is dominant, so this will pull it to 0. It doesn't matter. Negative 1 over a billion is still 0. It's just coming from the other side. So we see that this is the case where y equals 0, okay? Because the denominator is dominant. Here we got a constant value because the numerator and denominator were of the same value. Okay. All right, now we want to find any vertical asymptotes. Okay, so we know that the denominator cannot equal 0. Okay, so we take it out and we're going to set this equal to 0. Okay, so now let's solve this. So 8 is equal to x cubed, and now I'll take the cube root on both sides to undo this to get x is equal to 2. So we'll get a vertical asymptote when x is equal to 2. Okay? And we'll know this is a vertical because we could factor this x times x plus 4 over, I don't know if you remember how this is the difference of 2 cubes. So this factors into the cube root of the first, the cube root of the second. This first part is this one squared, which is 4. The last one's this one squared, which is x squared. And the middle term here applied is 2x. And then when factoring the difference of 2 cubes, remember we'll use SOAP, so we'll take the same the opposite, and always positive. Okay? So there's nothing common to cancel here, so this will lead to a vertical asymptote. Okay. Let's look at our third case. Okay. So for example, if we had h of x is equal to x squared minus 4x plus 1 over x plus 2. Now this will not factor. So if we looked at, for a vertical asymptote, well, I guess since we're talking about factoring, since that won't factor, we'll look at vertical asymptotes, yes. So the vertical asymptote in this case happens when the denominator goes to 0. So we get the equation x equals negative 2 will be a vertical asymptote. Now the horizontal asymptote is the y equals line, and we look at the dominant terms. So the dominant term of the numerator is x squared, while the denominator, its dominant term, is just x. So when you reduce these, this is equal just to the line y equals x. And if you wonder what happens as x gets really, really large, well, this is just going to infinity. So now we'd like to know, this is going to lead to a slant asymptote. And we'd like to know what exactly that asymptote is. To do that, we're going to use long division. Okay, so we're going to ask how many times does x plus 2 go into x squared minus 4x plus 1. So taking the first terms, x goes into x squared x times, then x times x is x squared, and x times 2 is 2x. And remember, we'll subtract, so we're going to change the signs. So this goes to 0, and we'll get negative 6x plus 1. Then we start again. How many times does x go into negative 6x? Well, that's minus 6 times. Then multiplying, we get minus 6x minus 12. But we need to change the signs. So now this goes to 0, and we have a remainder of 13. And so what has this told us? Well, the quotient here is the slant asymptote. Okay. So our quotient leads to the slant asymptote, and it's the line y is equal to x minus 6. Okay, so I think you have... So to graph these, you would go through the same process. You'd look for the horizontal asymptotes, the vertical asymptotes. X-intercepts, y-intercepts, and then plot some points. Okay. So let's do, I think this is one that we really should graph together. Okay. So let's say we had to graph this one. Okay, so we're going to graph h of x is equal to x squared minus 4x plus 1 over x plus 2. Okay. Now we've done the first steps. We see that we have a vertical asymptote where x is equal to negative 2, and that we have a horizontal asymptote of y is equal to x minus 6. Okay. Now we need to know the x-intercept. Okay. So that is, we have to set this function equal to 0 and solve it. Okay. So I want this x plus 2 out of the denominator, so I'll multiply through on both sides by x plus 2. So this will cancel. Okay. Leaving 4x squared, or I'm sorry, x squared minus 4x plus 1 equals 0. Okay. Now we have to solve this. This is a really good candidate for completing the square because this is negative, so let's do that. X squared minus 4x plus something. And let me move this 1 over. So minus 4 divided by 2 is negative 2. We have to take negative 2 and square that. And that's what we add to both sides. Now I know that this collapses into x minus 2 squared is equal to 4 minus 1 is 3. Taking the square root, we'll get x minus 2 is equal to plus or minus, don't forget that, root 3. So x is equal to 2 plus or minus root 3. Okay, so we have x-intercepts at 2 plus root 3, comma 0, and 2 minus root 3, comma 0. These are our x-intercepts. Let's find some y-intercepts. Okay, so for the y-intercepts, we have to find h of 0. Okay. So that is, we'll put in 0 squared minus 4 times 0 plus 1 over 0 plus 2. Okay. So h of 0 is just equal to 1/2. So we have a y-intercept of 0, comma 1/2. Okay, so let's think a little bit, because I want to try and put some of these points down here. Okay, I want an approximate value for 2 plus root 3. Okay, well, remember our little cheat sheet. If we have 0, 1, 2, 3, 4, okay, this is how our number line works. We're looking for an approximate value of root 3, so we can take the roots of all of these. Okay. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. Okay. So it's just a little bit less than 2. Okay. So this is approximately, so 2 plus root 3 is approximately 2 plus 1 point something. Okay. So that's approximately 3 point something. Now here, this we have 2 minus root 3. That's approximately 2 minus 1 and a little bit more, which is approximately point something. Okay, so it's still positive. Right? Like if this was 1.5, we'd get 2 minus 1.5, which would be 0.5. So this is a decimal. All right, but it's still positive. Okay, so let's see if we can see how this thing is going to look. Alright, so what do we know so far? Okay, well let's graph our asymptote that is y equals x minus 6. Okay. Okay, so we know that this is a line with an increasing slope of 1 that has a y-intercept of 0, negative 6. And if we let y equals 0, then x would also have to be equal to 6. 1, 2, 3, 4, 5. 4, 5, 6. Okay. Alright, so this is the point 6, 0. Right. Now it's just an asymptote, so I'm just going to dash it in. Okay. And now, what else do we have? We have a vertical asymptote at x equals 2, negative 2. Okay, so here's negative 2. So this is x is equal to negative 2. Okay. Now when you're sketching these, we'll extend this. It's okay once you've put in these 2 points to label everything else. Okay, so we have our x-intercepts. It's okay that it's going to be bounded in between here. Okay, so for down here, it's going to be bounded. I know nothing about these points, so I can just sketch it in. So as a sketch, that's okay. Right? Now up here, we know a few points. We know that the y-intercept is 0, comma a half. So we're going to look at that 0, comma 1/2. We also know that there was an x-intercept very, very close to here, which was 2 minus square roots of 3, comma 0. And then the other one was 3 and a little bit more. 1, 2, 3 and a little bit more. So this is 2 plus square roots of 3, comma 0. And now we'll just connect these dots. It's going to take off this way, come up this way. At some point in time, it's going to go over like this. So this is the one, how we would graph one with a slant asymptote. I'm just looking to see if we need to do another one. Okay, we graphed strawberries, we graphed with removable and non-removable. I suppose we should do one more. Okay, let's look at this one. We had f of x was equal to 4x over 5 times x minus 1, x minus 5. Okay, so in this case, we actually are going to get two vertical asymptotes. Right? So the domain is the set of all x such that x cannot equal 1 or 5 from before. So vertical asymptotes will happen when x equals 1, that line, and when x equals 5. What about these horizontal asymptotes? Well, what is the dominant term of the numerator? That's quite easy to see. The numerator is just 4x. So 4x will be the top. It's going to be the line y equals something. Okay, and then we're dividing by the dominant degree of the denominator. Now, so we have to look at this. If this was FOIL back out, we'd get an x squared term times 5. So the dominant term here is 5x squared. Right? 5 times x squared minus 6x plus 5. But once you distribute it through, we get 5x squared minus 30x plus 25. But we don't care about the rest of this. We just care about the dominant term. Okay. So if you were to reduce this, we get, excuse me, 4 over 5x. And here, the denominator still dominates. That is, if x goes to infinity, we're going to get 1 divided by infinity, which is just basically 0. So we know these things. Okay? So we know our vertical and horizontal. We need our x-intercepts. Okay? So that is, we have to find x over x minus 1, x minus 5. Where does that equal 0? Okay. So we multiply through by the denominator, 5 times x minus 1 times x minus 5 on both sides. Okay. So these denominators will cancel. This will still equal 0. So we get that 4x is equal to 0. So x has to be 0 divided by 4, which is just 0. Okay. So that's the x value, which leads to an x-intercept. When x is 0, y is 0. Okay. And what that means is it's also our y-intercept. Okay, because the origin is both, but we can do it both ways. Okay. So let's find f of 0, and that just becomes 4 times 0 over 5 times 0 minus 1 times 0 minus 5. So our numerator is 0. The denominator is 5 times negative 1 times negative 5. Okay. 0 divided by anything that's not 0 Well, that's just equal to 0. So again, the y-intercept also agrees because the origin is both the x and y-intercepts. Okay, let's plot what we have so we can get a look at it. Might turn my paper long ways for this one. Okay, so here we know we have an x and y intercept at 0, 0. We also have vertical asymptotes at x equals 1 and at x equals 5. The horizontal asymptote is y equals 0. Okay. And so in this case you can see that this is a case where this graph actually crosses the horizontal asymptote because it's in this very small area. It's not out here at infinities. Alright, what makes this harder now is that we have not just 4 areas to look at, but we have 6. So we're going to have to look at test points on all of them. And remember, graphs can behave erratically around values of the asymptote. Okay. So we're going to have to pick a value inside of here and evaluate this. Okay. So this is going to take some scratch work. Let's see what's happening at, say, x is equal to 1/2. Okay. So we put that back into the function, f of 1/2. So that is equal to 4 times 1/2 over 5 times 1/2 minus 1 times 1/2 minus 5. Alright, so up top, half of 4 is 2. Below we have 5. 1/2 minus 1 is minus 1/2. Okay. And 1/2 minus, now this is 10 halves, right? Is minus 9 halves. So this is equal to 2 over, this is 5 over 1. Negative and negative become positive. 5 and 9 are 45. And 2 and 2 are 4. So this is 2 times 4 over 45, which is 8 over 45. Okay. So this is very small, but it is positive. Okay. So at this point, we can label it here. And I'm still not convinced that this graph doesn't... Yes, I am. Okay. So it can't be coming this way because if the graph was going to come up, there'd be another x-intercept here. Okay. So now I've convinced myself that the graph is doing something like this. In between here and here. Now let's look at, like, say, negative 10 down here and see, does this graph cross and approach from this direction, or does it just jump and come out? So let's look at f of negative 10. So f of negative 10 is 4 times negative 10 over 5 times negative 10 minus 1 times negative 10 minus 5. So this is minus 40 over 5 times negative 11 times negative 15. So this is a positive 40 over a pretty big positive number. So in all, this is negative. So this is negative. Right? So I'm just doing some scratch work. So what that's telling me then is that down here we have something like this happening, like maybe it's doing something like that. Okay, and I guess I should actually figure out what this is. 15 times 11, 165, and then we have to multiply that by this 5, 25, 32, 185. Okay. So it's very, very, actually it's a little bit smaller than that, but we'll label it to make it true because just to make our graph. So it's coming very, very close that direction, going back up. Okay. Now we need to know what's happening at a value over here close to 1. So let's look at I guess 3 halves. You want to look at, let's look at 1.1 for fun. Let's do a decimal. Okay. So f of 1.1 is 4 times 1.1 over 5 times 1.1 minus 1 times 1.1 minus 5. Okay, so up top we get 4.4 divided by 5. 1.1 minus 1 is 0.1. 1.1 minus 5. Okay, so 5.0 minus 1.1 is 3.9, and we'll take the sign of the larger number. Okay. So this is 4.4 over, okay, so 5 times 0.1 is 0.5, and we have to multiply that by 3.9. The answer will be negative. Okay. To review how we multiply with decimals, 5 and 9 is 45. 5 times 3 is 15, plus 4 is 18. And then we count the decimal places. 1 decimal place, 2 decimal places. So this is negative 1.85. Okay. And now I'd like to think about this as, let's see, if I multiply by 100, if I multiply the top by 100, okay, what we get then is negative 185 over 440. Okay. And this is negative. Okay. If this was 200, we'd have 200 divided by 400. It's around negative 2. So it's somewhere down here because it's negative. Now, so I know it's taking off towards infinity this way. Now the question is it going like this, or is it going to cross and come up this way? Okay. Well, we know that since there's not another x-intercept here, this graph is not going to cross. So we can sketch in by logic that it happens like this. So now we just have one more area to check what's happening outside to the right of 5. Let's see what we can find out there. Okay. So, let's pick 10. So to that we have 4 times 10 over 5 times 10 minus 1 times 10 minus 5. 40 over 5 times 9 times 5, which is 40 over 25 times 9, it's 45, 18, 19, 20, 21, 22, 225. And that's positive. So from there we'll infer then at this point 10 comma 40 over 225. It's okay that I didn't reduce there. The graph will look like so. I should label this. We have 1.1 comma, what's that number? Negative 440 over 185. So, when there's 2 asymptotes and 3 regions to deal with, we have a lot more work to do. But I think that will get you through your homework, understanding how to do 1 over x, how to translate that, understanding about the powers of the numerator and denominator and how that plays into horizontal asymptotes. And then this process that we've done where you need to graph it, to graph the functions, we need to find vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts, okay, and then additional points as needed to determine the behavior of the graph. Okay. And finally, we'll have to know how to read the limits towards them. Okay, and that should get you through your homework. I'm sure you're going to have questions, so please email me.